So these are magnetic monopoles, okay? North, south, all right? They behave differently. They're two separate things here, right? And north and south, and they get interesting. So rather than it being a bar magnet like a dipole where one object has two polarities, these are independent and have their own polarity. Boing, boing. Okay, that's not what I was trying to find. This is what I was trying to find. All right. This is from physics.org. The alarm's going off. I don't know if you guys can hear it, but yeah, it's kind of a big deal here. August 14th, 2019. Breakthrough in understanding of magnetic monopoles could signal new technologies. Right? A breakthrough in understanding how quasi-particles known as magnetic monopoles behave could lead to the development of new technologies to replace electric charges. Researchers at University of Kent applied a combination of quantum and classic physics to investigate how magnetic atoms interact with each other to form composite objects known as magnetic monopoles. Based on the study of materials known as spin ices, the team showed how the hop from a monopole from one site in the crystal lattice of a spin ice to the next can be achieved by flipping the direction of a single magnetic atom. Although in theory at low temperatures the magnetic atoms do not have enough energy to do this, the team found that as a monopole arrives in a lattice site, it induces changes in the fields acting on the magnetic atoms surrounding it, which enable them to tunnel through the energy barrier. Dr. Quintanilla, I apologize, of the university's School of Physical Science said, "We found evidence that this mysterious low-temperature hopping is achieved through quantum tunneling, a phenomenon that allows quantum objects to overcome an obstacle which would, according to classical laws of physics, require more energy than the system has available to it. We showed that the magnetic atoms forming a monopole experience fields that are transverse to their own, which in turn induce the tunneling. We compute the monopole hopping rates resulting from this scenario and find them to be broadly consistent with available observations. The researchers suggest that this is a better understanding of monopole motion in spin ice materials that may enable future technologies based on moving magnetic monopoles rather than electric charges. Um, so a couple days ago, maybe was the 9th of April. Let's see. Yep, it was the 9th of April. We got this KP7 suddenly, like no one knew what it was about, and it surprised everyone. And then some people were like, "Oh yeah, it was expected this high speed, high solar wind speed. We knew that." Yeah, no, you didn't. No, you didn't. NASA didn't know. NOAA didn't know. No one knew. It just kind of happened. All right, and the solar speed index of that day was approximately 589 kilometers per second, which is a fast solar wind speed, but where did it come from? Just out of nowhere. And if we think about a coronal hole stream, typical coronal hole stream is anywhere between 500 and 800 kilometers per second for the wind speed. And so we tend to see that coming, and then there might be some little weird interferences, but none of that was happening. We need to understand that none of this is happening. This is the interplanetary magnetic field. This is the BT component. Look at that dip. It just dropped all of a sudden while this was pointing south, which resulted in a sudden climb from all of a sudden look, No predictions. Even severe at a high altitude, right? High latitude, pardon. Um, the most that they had seen in the forecast for the next day was a 4. We aren't looking for anything, and all of a sudden we're up till 7. Why did that happen? That happened because the BT component dipped. The B the BT component dipped, and that component is. I mean, look what happened. Look at this. This is a Schumann resonance. What? So that's like suddenly out of nowhere, this weird little sunspot group. I believe it was this one where there was no real mixing. There wasn't even an indicator that something would be going on, is what they're blaming it on. And I have to say, here's this. Quiet levels for the past 24 hours. Solar wind speed reached a peak of, here it is, 521 kilometers per second, and the total IMF reached 13, right? With a maximum southward component of -11, so that's south, okay? So electrons greater than 2 megavolts at geosynchronous orbit reached a peak of 334 PFU. All right, so basically it's the field dipped right here. The field dipped suddenly, unexpectedly, without warning. And I just wanted to like talk about that for a minute, because this is uncommon. All right, and it said 11, but here's it reading it at 12. Or no, sorry. Okay, my bad. This one and this one. It said that one went down to 13. Excuse me. So what's happening here is the polar field. Here's your BZ component, and when the BZ component tips downward into the south, all of the electron flow and proton charged particles get fed back down into the system. When the BZ is pointing north, they kind of flow out and away, right? And that's what gives us auroras, whether this thing is pointing north or south. And you got all these waves coming in from the sun, from other areas. If you think about this line as kind of like a boat, like it'll kind of like a little bit of flux wobbling up and down. But on Saturday, that thing went, and the wheel just tipped. All right. This one that's supposed to be the more steady of the two took a nosedive. And we can say it. It's fine. It happened. I was watching it happen in real time. And then I saw NASA and everyone else say, well, gee, that was unexpected. So don't be scared, and don't worry about admitting that we didn't know that it was going to happen. It wasn't in my prediction charts. That's for sure. My prediction charts have been pretty stable, pretty accurate up until this point. And that got weird. Okay, so that's one thing. See, here's how they look. When the solar flares happen and all of these things happen, we know they're coming. We can see them coming. But the other day, we did not, right? The KP index describes the disturbance of the Earth's magnetic field caused by the solar wind. All right, the solar wind. When you push a wave down, or you drop a book on the floor. Okay, how many times have you dropped a book on the floor and then the piece of paper next to it went flying off? Right? It kind of went flying off because the wind created by the force of the fall made the paper go. So it didn't need to come from the window. It came from the book. Do you see what I'm saying here? That wind didn't come from the sun. It was wind that was created by the tip in the field. You picking up what I'm putting down here? That's interesting. Let's see, look at this. Last month, we knew these were going to happen. And look, this is like a predicted storm. Like we knew this was going to happen. Long-term storm here. Went up to 6, dipped down to 5, come back up to 6. Knew that was going to happen. And I wish I'd have got the solar wind speed, an image of that for the day. Because KP5, KP6, we know this is happening. But here it's facing north. So we might get geoeffective activity, but we aren't getting the same type of auroras. Right? Solar flare detection. Well, this isn't the same day. I just wanted to check and see. And there's sometimes it bottoms out and there's none. None. All right. When excuse me. Try to cut that out. When the wind hits the field kind of dips a little bit, and we're able to detect that as it's coming in. Everything is on a circuit. Here's a cyclotron circuit. So there's a consistent amount of energy going into the field, right? But cyclotron radiation only allows for so much. If you use a synchrotron radiation, then it can, right here. How is a cyclotron different from a synchrotron? Both are accelerators. The cyclotron is a consistent magnetic field and a constant electric frequency. Okay? Whereas a synchrotron uses varying electric and magnetic fields and can accelerate particles to much higher energies. So we're going around now. This is the more descriptive of cyclotron frequency is more descriptive of what is happening here than synchrotron radiation, because it's this consistent feed, and we notice when it's different, and it behaves differently when it's different. It doesn't adapt and change like that. It has a reaction and then tries to recover, tries to come back to its real state, right? Its natural state. And we know this, they knew this, and we understand that this is how these things work. Again, north. Look, you got KP5 here, and you're only up to 6. 4. We're not getting reactions. We're not getting reactions from that. In the aurora, I should say, because we do tend to get earthquakes. Now, why does that happen? Why does that happen? Well, I'm going to go off an adventure and say something here that within everything in nature, you have a polarity, right? Positive, negative aspects, feminine, masculine aspects, the in, the out, the up, the down. Everything has its polarity, as does Earth, as does what's going on inside of the Earth, inside of the things. So you could have one single dipole in the center of the Earth that's creating this up and down positive and negative charge here, right? Or you could have a positive monopole and a negative monopole that are behaving together to create the field. And I wonder if that is the case, because here we have the thing's stuck. It wants you to know that this is a magnetic dipole within the Earth. Here are the two blobs. colossal blobs of molten rock hiding underneath Africa in the Pacific Ocean. So you got a polarity here. You've got a body, right? A charge, or what do you want to call it? A dipole. Let's call it a dipole. Underneath of an insulator. Giant insulator of land here, right? And this particular section of land is the largest landmass that is in the southern hemisphere. And it also is the largest continent. And it is home to large, vast swaths of sand deserts, so silicone, kimberlite mines, diamonds, other types of crystals that are created by pressure, right? Could that be electric pressure? On the other side, on the opposite side of this, we have the Ring of Fire, the Pacific Ring of Fire, and the dipole in the center of it. This saltwater saline conductive solution is on top of it, and therefore the charge has to be distributed and grounded to the closest ground, which is this ring of land going around. So as this electricity, as this energy is induced, it is fluid and conducted to the closest ground. And while that's happening, if it's piezoelectric effect, right? Positive, negative, positive, negative. Or it might be the other way around because this is the charge, but no, positive, negative, positive, negative. And then there's this back and forth, this oscillation between night and day when the sun, the solar energy is shining on the insulator and when the solar energy is shining on the conductor. And it oscillates back and forth, creating an electric field of its own via what's going on the surface and just above the surface in that electric dynamo atmosphere, electric atmospheric dynamo that is going on. And the poles are I want to say insulated, but they're white, right? They're cold. The heat is being taken and sent back down into the center. It's being moved away from these edges and being moved back down. Where did that picture go? I just had it. And being moved back, cycled back down into the center where it rotates, right? So you've got like this negative field and this positive field, and they're kind of hanging out together underneath of the surface. And then what's happening on top of the surface is this conduction that's creating a breathing effect, right? Just like we breathe. It's this oscillation. And because it's a independent dynamo created by the piezoelectric effect of this oscillating resonator, it is, I would say, diamagnetic because it isn't creating its own. This isn't ferromagnetics where the iron within the core would be creating this field. This is a different way of looking at this, where it's more of a geode. The interior of this planet is more of a crystal geode that's distributing the resonance, the energy from the resonance over its surface in order for it to maintain that frequency, which is what oscillating crystal resonators do. Sorry, drank pad. I went down the wrong tube. And so these are happening, and it's creating these stacks because that's also what happens in the crystal resonators. So, and then I was also thinking about the surface of the Earth and how, say, if it wasn't for the iron in this that we postulate is in the mantle and in the center of the Earth, which I'm not saying there is no iron, but I'm just wondering if it's actually to the amount of the amount of iron that we're postulating, because we're saying that that's what's creating the charge, that's what's creating the field, and it isn't necessary for it to be creating a field. All we need is this fluid motion of the resonance if the energy is being delivered to us via another source, which it is via the sun, right? And then our own mechanical behavior um, perpetuates it, right? Because we think about Mars, and Mars is the red planet because it's iron, and it doesn't have a field. It doesn't have a field. And then we think about Venus, and Venus is alive and active. Obviously, it's got a atmosphere. It's sulfuric. It's got a heavy duty pressure. I mean, 89 times the pressure of the surface of Earth, and no field. And it is moving very, very slowly. It rotates around, and it's one Venus day, it takes almost an entire rotation around. So it's almost like a tidal lock if you think about it with the sun. But there's no release of that energy. That dynamo is like, it's just kind of like keeping whatever and internalizing it and creating pressure within the sphere there. And then Mercury has a field, right? Mercury has hardly any atmosphere. It's right up next to the sun. It's a very, very, very small, almost like you'd think minute, like particle next to the giganticness of the sun, and yet it has a current. It has a magnetic field. It goes in a little ring around its center. And it doesn't work in the same way that Earth's magnetic field works. And then we can also think about the fact that there's a lot of gold on Earth, and gold is an excellent insulator and a conductor. And it's a natural, it's like the best natural conductor. And according to some of the research that I did a while back, there's an exponential amount more gold on the planet Earth than there is in the rest of the solar system. Right? The abundance of gold on Earth's crust is 4 parts per billion by weight, compared to 1 part per billion by weight in the solar system. All right, and gold is diamagnetic, and it is produced through these veins when quartz crystals react to a charge during an earthquake, right? During the pressure and the charge, and the earthquake happens, and voila, all of a sudden you get gold deposits because there's a conduction happening there within the insulator, right? Within the silicate quartz body there of the oscillating resonator, there's conduction happening. But nothing is gained and nothing is lost because it's the gold. It actually helps regulate that resonance. It gets really, really, really weird and interesting. And I think that this is a good place to kind of pause this and think about those things, and then we can move on to the next section. Because it just continues to get weirder, but this is all really relevant compared to relevant for what goes on next. In order for what we're going to talk about next to make sense, we have to allow this scenario into our imagination. So I'm just going to leave it here, and we'll think about this for a little while, and then once we've ingested some of it, we'll come back and we'll talk about it more. Awesome. Thanks, guys.